These are the answers to the AP Chemistry packet on topics 9.1 to 9.7. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now let's take a look at our first multiple choice question. Question 1 says the following. Which of the following equations represents a reaction for which the standard entropy change is negative? That is, the value of delta S is less than 0. So this question falls under topic 9.1, Introduction to Entropy. And this first essential knowledge statement says, entropy increases when matter becomes more dispersed. For example, the phase change from solid to liquid or from liquid to gas results in a dispersal of matter as the individual particles become freer to move and generally occupy a larger volume. Similarly, for a gas, the entropy increases when there is an increase in volume at constant temperature, and the gas molecules are able to move within a larger space. And for reactions involving gas phase reactants or products, the entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. Now, everything I read in that essential knowledge statement refers to an increase in entropy. But in fact, in question 1, we're actually looking for a reaction that involves a decrease in entropy. So 3 of these 4 choices will show an increase in entropy, and those will be incorrect, and only 1 of these 4 choices will show a decrease in entropy. Let's go ahead and look for phases of matter among these 4 choices. Now, in choices A and B, we can see that all of the reactants and all of the products are in the gas phase. So for choice A, if I count up the total moles of gas on each side of the equation, I can see 3 moles of gas on the left and 2 moles of gas on the right. And in choice B, I can see 2 plus 7, so that would be 9 moles of gas on the left, and then I see 4 plus 6, that would be 10 moles of gas on the right. Now, with choices C and D, there are definitely gases involved, but there's also solids and aqueous particles as well. So in choice C, I see 1 mole of solid and 2 moles of aqueous particles on the left, and I see 1 mole of aqueous particles and 1 mole of gas on the right. And then finally in choice D, I see 1 mole of solid on the left, and I see 2 plus 1 plus 1, I see 4 moles of gas on the right. So remember, 3 of these 4 choices involve an increase in entropy and would be incorrect. Only 1 of these choices involves a decrease in entropy. So I'll just highlight what I had read earlier, which is for reactions involving gas phase reactants or products, the entropy generally increases when the total number of moles of gas phase products is greater than the total number of moles of gas phase reactants. So starting with choice B, I go from 9 moles of gas to 10 moles of gas. That is an increase in the total number of moles of gas, so that would be an increase in entropy, so choice B is incorrect. Now in choice C, the only gas that I see is on the right side of the equation, so I start with 1 mole of solid and 2 moles of aqueous, and on the right, I have 1 mole of aqueous and 1 mole of gas. Definitely an increase in the number of moles of gas, so I can eliminate choice C because that would also involve an increase in entropy. And then finally in choice D, 1 mole of solid is being transformed into 4 moles of gas. That is definitely an increase in the number of moles of gas, and that would be an increase in entropy, so I can eliminate choice D. Well, that means that choice A, going from 3 moles of gas to 2 moles of gas, is the correct answer. So in choice A, in that particular equation for that reaction, the total number of moles of gaseous products is less than the total number of moles of gaseous reactants. So the particles on the product side of the equation on the right have a smaller number of possible arrangements than the particles on the reactant side of the equation on the left. So the correct answer to question 1 is choice A. Now let's take a look at question 2. Question 2 is similar to question 1 in that we're talking about a change in entropy, but in question 1, we were looking for a decrease in entropy with a negative value for delta S. And here in question 2, it says which of the following particulate representations represents the change with the greatest positive value of delta S. So in question 2, we're looking for an increase in entropy. Let's begin by focusing on the phases of matter that are represented in these particulate representations. So all of the phases of matter are either solid or gas in these particulate representations. So starting with choice A, I see gas on the left and I see gas on the right. And if I count the particles, I see the same number of particles on each side. So 8 gas particles on the left and 8 gas particles on the right. Now we're looking for the change with the greatest positive value of delta S. So there is no increase in the number of gas particles in choice A, so we would expect a very small change in entropy. It might be slightly positive or slightly negative, so it doesn't appear that choice A would be the correct answer. Now moving on to choice B, we have solid particles on the left and we have gaseous particles on the right. So it goes from solid to gas. That would involve an increase in entropy. Now, moving on to choice C, I see gas particles on the left, and I see a mixture of solid and gas particles on the right. So going from all gas to a mixture of solid and gas, that would involve a decrease in entropy. So we can eliminate choice C, looking for the change with the greatest positive value for delta S. And then finally, moving on to choice D, we start with all solid on the left, and then we have a mixture of a solid and a gas on the right. So going from all solid to a mixture of solid and gas, that would also involve an increase in entropy. But I can go ahead and eliminate choice A because we would expect a very small change in entropy. And I can eliminate choice C because the actual change in entropy would be negative. There's a decrease in entropy. So now I've narrowed down my choices to either choice B or choice D. And if I count the gas particles on the right side of the arrow, I see 8 gas particles that are formed from a solid in choice B. And then because in choice D I have a mixture of a solid and a gas, I actually see a smaller number of gas particles that are formed in choice D. So if I'm looking for the change with the greatest positive value of delta S, choice B should be the correct answer. Starting with a solid and then completely transforming that solid into a gas, that's going to be a greater change in entropy than in choice D, where we start with all solid and then we transform that into a mixture of a solid and a gas. So choice B is the correct answer because of the 4 choices. After the change in choice B, then these particles have the larger number of possible arrangements. So choice B is the correct answer to question 2. Now let's take a look at question 3. In question 3, we are given a data table and it says the values of the standard molar entropies of 3 different substances are listed in the following table. Based on this information, which of the following is closest to the value of delta S for the reaction represented by the following equation? So we are given a balanced chemical equation involving 1 mole of chlorine, Cl2, reacting with 2 moles of nitrogen monoxide, NO, and it produces 2 moles of nitrosyl chloride, which has the chemical formula NOCl. So as you can imagine, this will involve a calculation. This question falls under topic 9.2, absolute entropy and entropy change. The entropy change for a process can be calculated from the absolute entropies, which are also known as the standard molar entropies of the species involved before and after the process occurs. So the delta S for the reaction is equal to the sum of all of the standard molar entropies of the products minus the sum of all of the standard molar entropies of the reactants. Let's go ahead and do that calculation. So it's going to be products minus reactants. Now we only have one product, that would be the nitrosyl chloride, NOCl. It has a value of 262 joules per Kelvin mole, but there is a coefficient of 2 in the balanced equation. So it's going to be 2 times 262 for the calculation for the products. Now moving on to the reactants, we have both chlorine, Cl2, which has a value of 223 joules per Kelvin mole. And then we have the nitrogen monoxide, which has a standard molar entropy of 211 joules per Kelvin mole, but there is a coefficient of 2, so we have to multiply that number by 2. So for the reactants, it would be 223 plus 2 times 211. So when we do that math, we get 524 for the products and 645 for the reactants. So 524 minus 645 gives us a value of negative 121, and the units are joules per Kelvin mole of reaction. So the correct answer to question 3 is choice B. Now let's take a look at question 4. Now question 4 is similar to question 3 because it will also involve that equation with entropy and products minus reactants. But the difference between question 3 and question 4 is that in question 4, we're not going to be calculating the delta S for the reaction. Instead, we're going to be calculating the value of the standard molar entropy for the product of this reaction. So question 4 says, the formation of gaseous hydrogen bromide, which has the formula HBr, from hydrogen gas, H2, and bromine vapor, Br2, is represented by the following equation. And as you can see, the delta S for this reaction is given to us as 20 joules per Kelvin mole of reaction. It goes on to say that the values of the standard molar entropies of the reactants, so hydrogen and bromine, are listed in the following table. But the question asks, which of the following is closest to the value of the standard molar entropy for hydrogen bromide, HBr? Let's go ahead and set up that same equation that we used in question 3, so that delta S for the reaction is equal to the sum of the standard molar entropies for the products minus the sum of the standard molar entropies for the reactants. Now we know that HBr is the only product listed, but since we don't know that value for the standard molar entropy of HBr, I'm going to go ahead and call that X as an unknown variable. I'm going to use the number 2 as the coefficient, so it's 2X for the products of this chemical reaction. Now, the reactants are hydrogen and bromine, and we don't have any coefficients to worry about, so for the reactants, it would be the number for hydrogen, 130, and the number for bromine, 250. So right now, I have the delta S for the reaction, which was given to us as 20 joules per Kelvin mole of reaction. So 20 is equal to 2X minus 380. All I have to do now is solve for X. So if 20 equals 2X minus 380, then 2X is equal to 400, and then that means that X is equal to 200. So the correct answer to question 4 is choice B. The standard molar entropy of HBr is 200 joules per Kelvin mole. All right, now let's take a look at question 5. In question 5, we are given a balanced chemical equation in which carbon monoxide gas, so CO, reacts with ozone gas, O3, and it produces carbon dioxide gas, CO2, along with oxygen gas, O2. In addition to the balanced chemical equation, we are given the value of delta H and the value of delta S for this reaction. So the value of delta H is equal to negative 426 kilojoules per mole of reaction, and the value of delta S is equal to negative 18 joules per Kelvin mole of reaction. So we are going to involve calculations in this question with delta H and delta S, so please pay attention to the units. Note that delta H has kilojoules and delta S has joules. That's very important. All right, let me go ahead and read question 5. It says the reaction between carbon monoxide gas and ozone gas is represented by the equation shown above. Which of the following is most likely to be true about this reaction at 298 Kelvin? So all 4 of these choices involve delta G as well as T delta S. So this question falls under topic 9.3, Gibbs free energy and thermodynamic favorability. And one of the essential knowledge statements that I'm highlighting on this slide says, knowing the values of delta H and delta S for a process at a given temperature allows delta G to be calculated directly using the equation delta G equals delta H minus T delta S. This equation is featured on the AP Chemistry equations and constant sheet. So let's go ahead and use that equation right now. And this slide that you're looking at is actually from my previous video for topic 9.3, and I'm just highlighting that comment that I made earlier. Pay attention to the units in your calculations. The units of delta H have kilojoules, and that would be different than the units of delta S, which are joules per Kelvin mole of reaction. So again, pay attention to kilojoules and joules. Otherwise, if you ignore those units, then you could have an incorrect answer. All right, so back to question 5. Delta G equals delta H minus T delta S. Now the T, the temperature, will be 298 Kelvin. The delta H is what we are given in this question, so negative 426 kilojoules per mole of reaction. So minus T delta S, and notice that I'm showing divide by 1,000 to go from joules to kilojoules. So negative 18 now becomes negative 0.018 with units of kilojoules per Kelvin mole of reaction. And again, there's my 298 Kelvin for the temperature. So when I do this math, I have negative 426 and then minus the product of 298 times negative 0.018. So negative 426 minus negative 5.4, and notice that the Kelvin cancels out in terms of a unit, but I have kilojoules and kilojoules per mole of reaction. So my final answer is negative 421 kilojoules per mole of reaction. The fact that delta G has a negative value means that I've narrowed down my choices. It's either A or B, because in choices C and D, they say that delta G is positive, but we know that delta G is negative 421. Now, with respect to the T delta S term, that would be 298 times negative 0.018, and that works out to be negative 5.4. So the magnitude, I'm referring to the absolute value of that number. So the magnitude of T delta S would be 5.4. So the absolute value of negative 5.4 is 5.4. And then the magnitude, the absolute value of delta H, would be 426. So the magnitude of T delta S is smaller than the magnitude of delta H, and so that makes choice A the correct answer. So the answer to question 5 is choice A. Now let's take a look at question 6. In question 6, we are given 4 different chemical reactions, and we are also given both the value of delta H and the value of delta S for each one of these reactions. And the question says, which of the following reactions is not thermodynamically favored at low temperatures, but becomes favored as the temperature increases. So this question also falls under topic 9.3, Gibbs free energy and thermodynamic favorability. And as you can see highlighted on this slide, there are 4 different possibilities with respect to the signs of delta H and delta S. So I'm going to go ahead and present what I had presented in my video that included topic 9.3. Let's go through all 4 of these possibilities. Remember that if delta G is negative, then the process is thermodynamically favored. Otherwise, if delta G is positive, then the process is not thermodynamically favored. So I'm going to start with the possibility in which delta H is positive and delta S is negative. So mathematically, the sign of delta G would be positive at all temperatures, no matter what. So that process with a positive delta H and a negative delta S would not be favored at any temperature. Now, moving on to the next possibility, what if delta H is negative and delta S is positive? So mathematically, the delta G would always be negative no matter what the temperature is. So that process with a negative delta H and a positive delta S would be favored at all temperatures. Now we come to the next 2 possibilities in which the sign of delta H and delta S are either both positive or both negative. So if delta H is positive and delta S is also positive, now the sign of delta G depends on how large or how small the value of temperature is. So at low temperatures, the value of delta G would be positive and the process would not be thermodynamically favored. But then at high temperatures, the sign of delta G would become negative and the process would be favored. All right, finally, the last possibility would be what if both delta H and delta S are negative? So in that situation, the sign of delta G would again depend on the magnitude of T, the temperature. So if delta H and delta S are both negative, then this process would be favored at low temperatures where delta G would be negative, but then it would become not favored at high temperatures because delta G would be positive. Let's go back and read question 6. It says, not thermodynamically favored at low temperatures, but becomes favored as the temperature increases. So it's going to be this possibility, only favored at high temperatures. So not favored at low temperatures, only favored at high temperatures. We need the sign of delta H and delta S to both be positive. And so now looking at the 4 choices, the correct answer to question 6 is choice B, involving a positive delta H and a positive delta S. And under those conditions, the process would be thermodynamically favored only at high temperatures. All right, the correct answer to question 6 is choice B. Now let's take a look at question 7. In question 7, it says, when water is added to a mixture of solid sodium peroxide, Na2O2, and solid sulfur, a redox reaction occurs as represented by the equation below. So in addition to the balanced chemical equation, we are also given the value of delta H and the value of delta S for this reaction. And the question asks, which of the following statements about the thermodynamic favorability of the reaction at 298 Kelvin is correct? And we can see words such as unfavorable and favorable, and we can see words such as driven. So driven by delta S, driven by delta H, or driven by both delta H and delta S. So on the next slide, I'm going to present what I had presented in my video for topic 9.3. So this is driving forces that support the thermodynamic favorability of a process. Now, you can think of a driving force as a feature of a physical or chemical process that helps to explain why that process is thermodynamically favored to occur. And there are two possibilities for a driving force. If the process is exothermic, that is, the sign of delta H is negative, then this could be a driving force to explain why the process is thermodynamically favored to occur. Or if the process involves an increase in entropy, that is, the sign of delta S is positive, this could also be a driving force to explain why the process is thermodynamically favored to occur. And another way to think about the driving force of a process is to look at the signs of delta H and delta S for that process and ask yourself the following question. Does the sign of delta H or delta S cause the value of delta G to be negative? So a negative delta G indicates that the process is thermodynamically favored. So a negative delta H or a positive delta S, that would support mathematically the value of delta G would be negative. So a negative delta H could be a driving force. A positive delta S could also be a driving force. But on the other hand, if the process is endothermic, that is delta H as a positive sign, a positive delta H cannot be a driving force to explain why the process is thermodynamically favored to occur. And then also, if the process involves a decrease in entropy, that is, the sign of delta S is negative, this also, a negative delta S, cannot be a driving force to explain why the process is thermodynamically favored to occur. So the only two possibilities for a driving force would be a negative delta H or a positive delta S. Let's go back and look at question 7. So we have a negative delta H, which could be a driving force, but we have a negative delta S, and that cannot be a driving force. So based on that information, let's go ahead and eliminate choice B, because it says driven by delta S only, and that's not a possibility. And then in choice D, it says driven by both delta H and delta S. And again, the delta S negative cannot be a driving force, so we can eliminate choice D. Now that we've narrowed it down to either choice A or C, let's do the math and determine whether the sign of delta G is positive or negative. We have kilojoules for delta H, and we have joules for delta S. So I'm going to go ahead and divide the delta S by 1,000 like I did earlier. So I have negative 610 kilojoules per mole of reaction for my delta H minus T delta S. So the temperature is 298 Kelvin, and my delta S, now that I've converted it into kilojoules, is negative 0.0073 kilojoules per Kelvin mole of reaction. So when I do this math, I get that the delta G has a negative value. It's negative 608 kilojoules per mole of reaction. So because delta G is negative, then this process is thermodynamically favored to occur. So the correct answer is choice C. It is thermodynamically favorable, and it is driven by delta H only. All right, correct answer to question 7 is choice C. Now let's take a look at question 8. In question 8, we are given a balanced chemical equation for a reaction in which carbon monoxide gas, CO, reacts with hydrogen gas, H2, to produce methanol vapor, which has the chemical formula CH3OH. We are also given information about the sign of delta H and delta G. We are told that delta H is negative, so less than 0, and that delta G is negative, less than 0, at 298 Kelvin. And so the question says a 1.0 mole sample of carbon monoxide gas and a 1.0 mole sample of hydrogen gas are placed in a previously evacuated 10-liter vessel at 298 Kelvin. And even though the reaction represented by the equation above is thermodynamically favorable, the formation of methanol vapor, the product, is not observed. Which of the following best explains why the product, methanol vapor, is not produced at 298 Kelvin? So this question falls under topic 9.4, thermodynamic and kinetic control. And with respect to the essential knowledge statements, the first one says, many processes that are thermodynamically favored do not occur to any measurable extent, or they occur at extremely slow rates. Processes that are thermodynamically favored but do not proceed at a measurable rate are under kinetic control. High activation energy is a common reason for a process to be under kinetic control. On this slide, you can see two different energy diagrams, and one has a smaller magnitude for the activation energy. So a lower magnitude for the activation energy is associated with a faster reaction rate. And then the other diagram has a higher magnitude for the activation energy, and that would be associated with a slower reaction rate. But this says nothing about the value of delta H or delta S or delta G. So we're only talking about a slow reaction rate being associated with a high activation energy. So it's not about the delta H or the delta S or the delta G. It's simply about the activation energy for that reaction, resulting in a slow reaction rate. All right, I'm going to start with choice D and then work my way up to choice A, looking at these four choices. So choice D says the rate of the reaction is extremely slow because the value of delta H is negative. But as I just mentioned, a delta H or a delta S or a delta G, that tells us nothing about the activation energy or the reaction rate. So simply knowing that the value of delta H is negative, that just means that the process is exothermic. But this tells us nothing about the activation energy or the rate, so I'm going to eliminate choice D. Now, choice C says that the carbon monoxide and the hydrogen must be mixed in a 1:2 mole ratio in order for the reaction to occur. But when reactants are combined in a chemical reaction, you could have a limiting reactant, you can have an excess reactant. There is no rule that says that the reactants must be combined in a ratio that matches their coefficients in the balanced equation. So we don't need a 1:2 mole ratio for these reactants in order for the reaction to occur. So I can eliminate choice C. Now choice B says that at 298 Kelvin, some of this methanol vapor, which is the product of this reaction, must first be present in the vessel in order for the reaction to occur. So methanol vapor is a product, but the products of a chemical reaction do not need to be present in the vessel in order for the reaction to occur. So hopefully you can see why I began with choice D and then worked my way up. The correct answer to question 8 is choice A. Remember, we're talking about a high activation energy for the reaction that leads to a very slow reaction rate. So if a process is thermodynamically favored and the formation of the products is not observed, a common explanation is that the reaction has a high activation energy. So when the reactant particles collide, the energy of most of these collisions is lower than the activation energy for the reaction. So the correct answer to question 8 is choice A. At 298 Kelvin, the energy of most molecular collisions is lower than the activation energy for the reaction. So a very slow reaction rate, a very high activation energy is the explanation. All right, well, that is the answer to question 8. Now, let's take a look at question 9. We are given a balanced chemical equation involving 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to produce 2 moles of water vapor. We are given that the sign of delta H is negative. It's negative 484 kilojoules per mole of reaction. And we're also given that the sign of delta S is negative. It's negative 89 joules per Kelvin mole of reaction. And question 9 says the following. When hydrogen gas and oxygen gas are mixed together in a rigid reaction vessel at 298 Kelvin, no reaction occurs. So this question also falls under topic 9.4, which is thermodynamic and kinetic control. So it goes on to say, when the mixture is sparked, however, the gases react vigorously according to the equation above. So which of the following statements correctly explains why the spark is needed for the reaction to occur when the gases are originally at 298 Kelvin? So I'm going to begin by calculating the value of delta G for this reaction because it's important to know whether the sign of delta G is negative or positive. Is this reaction thermodynamically favorable at 298 Kelvin? Again, watch out for your units. We have kilojoules for delta H and joules for delta S. So when I do this math involving delta H minus T delta S, I get negative 484 kilojoules per mole of reaction minus 298 Kelvin times negative 0.089 kilojoules. Again, I changed that value of delta S into kilojoules by dividing by 1,000. So when I do that math of negative 484 minus the product of 298 times negative 0.089, I get that delta G has a value of negative 457 kilojoules per mole of reaction. Delta G is negative. The process is thermodynamically favored. So I can eliminate choice A, which says that the reaction is not thermodynamically favorable. So that's false. Now, moving on to choices B and C, they talk about the reaction rate is very slow. Is it because delta H is negative? Is it because delta S is negative? No. Looking at the signs of delta H or delta S, that tells us that the reaction is exothermic, negative delta H, or that the entropy is decreasing, going from 3 moles of gas to 2 moles of gas, but that tells us nothing about the activation energy or the reaction rate. So I can eliminate choices B and C. Now the correct answer is choice D, and as it says in topic 9.4, high activation energy is a common reason for a process to be under kinetic control and having a very slow reaction rate. So the correct answer to question 9 is choice D. The reaction has a large activation energy, so that spark is needed to overcome the activation energy for those collisions. All right, question 9 is choice D. Now let's take a look at question 10. In question 10, we are presented with 3 different chemical equations, and the question says, on the basis of the information above, the dissolution of solid iron fluoride, which has the chemical formula FeF2, in acidic solution is, and our choices include thermodynamically favorable or not thermodynamically favorable, and then we have justifications involving a particular equilibrium constant K being either greater than 1 or less than 1. So this question falls under topic 9.5, free energy and equilibrium. So the first highlighted essential knowledge statement says, the phrase thermodynamically favored, in which the sign of delta G is negative, means that the products are favored at equilibrium, in which the value of the equilibrium constant K is greater than 1 under standard conditions. And then that last one that's highlighted on this slide says that processes with a negative delta G favor the products, that is, the magnitude of the equilibrium constant is greater than 1. And on the other hand, processes with a positive delta G would favor the reactants, that is, the magnitude of the equilibrium constant K would be less than 1. Now let's go back and take a look at question 10. That third equation that is listed here is the dissolution of solid iron fluoride in acidic solution. So what we're going to do is determine how the first two equations could be combined in a certain way to produce the third equation. So almost like a Hess's law problem. Can we combine equations 1 and 2 to equal equation 3? So the first thing I'm going to focus on is that iron fluoride compound, FeF2. Now I see 1 mole of FeF2 on the left, and in the first equation, I also see 1 mole of FeF2 on the left. So nothing has to be done to that first equation in any way. So this equation remains unchanged. Now moving on to the acidic solution involving the presence of aqueous H+ ions. In this overall chemical equation at the bottom, I see 2 moles of H+ on the left, but the equation involving H+, there's only 1 H+. That means that this particular equation needs to be multiplied by 2. So if I multiply that equation by 2, I have to ask the question, what will happen to the value of the equilibrium constant K when a chemical equation is multiplied by 2? Now, to answer that question, it goes back to Unit 7, equilibrium. So topic 7.6, properties of the equilibrium constant. When the stoichiometric coefficients of a reaction are multiplied by a factor n, then the equilibrium constant K for the modified equation is equal to the original value of K, not multiplied, but raised to the power n. And then it also goes on to say that when reactions are added together, then the K, the equilibrium constant of the resulting overall reaction, is not the sum, but the product. So multiplying the individual K values for the reactions together. Now I'm going to go ahead and raise the K value to the second power, which means that this number needs to be squared. And so 10 to the third power squared becomes 10 to the 6. So 1 times 10 to the 6, and then my coefficients will all be 2, 2, and 2. So I've doubled all of the coefficients, and my new value of K is 1 times 10 to the third squared, which becomes 1 times 10 to the 6. Now remember, we don't add the K values together, we actually multiply the K values together. So when I add these two equations together, then the product of 2 times 10 to the negative 6 times 1 times 10 to the 6, that will give me the overall equilibrium constant for that third reaction. And when I do that math, I literally get the number 2 when I multiply 2 times 10 to the negative 6 times 1 times 10 to the 6. Now, how does the number 2 help me answer this question? Well, remember that if K is greater than 1, then the process will be favorable with a negative delta G. Otherwise, if K were less than 1, then the process would not be favored with a positive delta G. So 2 is greater than 1, so the dissolution of solid iron fluoride in acidic solution is thermodynamically favorable, because the equilibrium constant is greater than 1, so therefore the delta G would be negative. So the correct answer to question 10 is choice B, thermodynamically favorable, because K3, the equilibrium constant for the overall reaction, is greater than 1. All right, now let's take a look at question 11. In question 11, it says a reaction is known to have a negative value of delta H and a negative value of delta S. And the question asks, which of the following statements correctly describes the equilibrium constant, KEQ, for this reaction? Now, back to this particular slide that I had mentioned earlier, we have a negative delta H and a negative delta S. So will this reaction be favored at all temperatures, high temperatures, or low temperatures? Well, with a negative delta H and a negative delta S, then the sign of delta G will only be negative and therefore favored at low temperatures. But at high temperatures, then the sign of delta G becomes positive and it's not favored. So it's favored at low temperatures. And if it's favored at low temperatures, delta G will be negative at low temperatures. Otherwise, delta G will be positive at high temperatures. So favored at low temperatures would mean that the K value is greater than 1. So if a negative delta G corresponds to a K value greater than 1, whereas a positive delta G corresponds to a K value that's less than 1, then we have K will be greater than 1 at low temperatures when delta G is negative. K will be less than 1 at high temperatures when delta G is positive. So I can conclude that the correct answer to question 11 is choice C. It will be favored. The process is favored at low temperatures, so K will be greater than 1 only at low temperatures. So again, correct answer to question 11 is choice C. Now let's take a look at question 12. In question 12, we are given several different particle diagrams, and it says the process of dissolution of solid sodium chloride in liquid water is represented in the diagram above. And the question asks, which of the following summarizes the signs of delta H and delta S for each part of the dissolution process? So there are three different processes that we can see listed, and they are breaking solvent-solvent interactions. In other words, breaking attractive forces between liquid water molecules. We can see breaking solute-solute interactions, and that would involve breaking the attractive forces between the sodium ions and the chloride ions in that solid sodium chloride, the solute, and then finally forming solute-solvent interactions. So forming ion-dipole attractive forces between the water molecules and the ions of the solute. So this question falls under topic 9.6, free energy of dissolution. The free energy change, or the delta G, for the dissolution of a substance reflects a number of factors. The breaking of the interparticle attractions that hold the solid together, the reorganization of the solvent around the dissolved species, and the formation of interparticle attractions between the solute and the solvent. So in my video for topic 9.6, I had presented this diagram involving step 1, step 2, and step 3. So step 1 involves breaking the attractive forces between the particles of solid. And so when that occurs, the particles are more dispersed. So breaking attractive forces is an endothermic process. That's a positive delta H. And when the particles are more dispersed, the entropy increases, and so that's a positive delta S. In step 2, you're also breaking some of the attractive forces between the molecules of the solvent. The particles are slightly more dispersed. Again, an increase in entropy, so positive delta H, positive delta S. But then in step 3, we are forming attractive forces between the particles of the solute and the particles of the solvent. So forming attractive forces is an exothermic process. That's a negative delta H. And now the particles are slightly less dispersed or more ordered. That would be a negative delta S. So in my video for topic 9.6, I had asked this particular question. So in step 1 and step 2, attractive forces are broken and the particles become more dispersed. So we have a positive delta H and a positive delta S for step 1 and step 2. But in step 3, attractive forces are formed and the particles become less dispersed or more ordered. So we have a negative delta H and a negative delta S. So this question is very similar to the question that we are about to answer in this packet. So breaking attractive forces is endothermic. That means I'm looking for a positive delta H. And then forming attractive forces is an exothermic process that would be a negative delta H. So the only choices that have a positive delta H for breaking and a negative delta H for forming are choices A and B. So we can eliminate choices C and D for that reason. Now, what about the entropy or the delta S? Well, when you form attractive forces, that would be particles are slightly less dispersed and more ordered. So that would involve a negative delta S. And so that's why the correct answer to question 12 is choice A. So positive delta H for breaking attractive forces, positive delta S for breaking attractive forces, negative delta H and negative delta S for forming attractive forces. So the correct answer to question 12 is choice A. Now let's take a look at question 13. In question 13, it says the following. Based on the values of delta G for the three reactions represented above, what is the value of delta G for the reaction represented below? So this question falls under topic 9.7, coupled reactions. A desired product can be formed by coupling a thermodynamically unfavorable reaction that produces that product to a favorable reaction. And in the coupled system, the individual reactions share one or more common intermediates, and the sum of the individual reactions produces an overall reaction that achieves the desired outcome and has a delta G less than 0. So effectively, we're talking about a Hess's law problem. Now, this is similar to question 10 in this packet, which was also a Hess's law type problem. But back in question 10, we were looking at the equilibrium constants, K. But in this question, question 13, it's about the delta G values. But you can think of this as a Hess's law problem. What do we have to do to combine reactions 1, 2, and 3 to achieve this overall reaction that you can see inside that red box near the bottom of the slide? So I'm going to start with 4 moles of NH3. So I'm looking for a reaction that contains NH3, and that would be reaction number 1. But reaction number 1 also has 4 moles of NH3 on the left. That's exactly where it should be. So reaction 1 remains unchanged. Now the delta G for reaction 1 is negative 1011 kilojoules per mole of reaction. So that value remains unchanged, negative 1011. Now I'm going to move on to a chemical that's on the right side of this equation, and that would be, I see 4 moles of HNO3 on the right. So I'm looking for HNO3, and I can see it in reaction 3. It's exactly where it needs to be. I see 4 moles of HNO3 on the right, so reaction 3 also can remain unchanged. The delta G for reaction 3 is negative 166 kilojoules per mole of reaction, so that value remains unchanged. Now I have a problem in that I'm looking for NO2 in reaction 2. However, NO2 does not appear in the overall balanced chemical equation. So what we need to do is actually cancel out the NO2. So I see 4 moles of NO2 on the left in reaction 3, and I see 2 moles of NO2 on the left in reaction 2. So what am I going to have to do to reaction 2 to get those NO2 molecules to cancel out? I need 4 moles of NO2 on the right, which means that reaction 2 is going to be reversed, and reaction 2 is also going to be multiplied by 2. So reaction 2 is going to be reversed to get the NO2 on the other side of the equation, but I need a coefficient of 4, which is why I also have to double that equation. So here comes the change to reaction 2. So now I have reversed it, so I have 4 moles of NO and 2 moles of O2, which are now on the left, and I have 4 moles of NO2 on the right, which is exactly what I need to get the NO2 to cancel. But what happened to my delta G? Well, it was 71 kilojoules per mole of reaction. But if I reverse that reaction, the sign of delta G will change. And if I double all of the coefficients, I have to double the delta G. So now the delta G changes from positive 71 to negative 142 because that reaction was both reversed and multiplied by 2. Let me just confirm that after making these changes, actually the one change to reaction number 2, let's make sure that everything that is supposed to cancel out is canceled out. So 4 moles of NO on the left, 4 moles of NO on the right, 4 moles of NO2 on the left, 4 moles of NO2 on the right. Now, what about 8 moles of oxygen? So we haven't talked about oxygen. Let's see if I have 8 moles of oxygen on the left. 5 plus 2 plus 1. That is a total of 8 moles of oxygen, so that looks good. And then what about the water? I see 2 moles of water on the left, and I see 6 moles of water on the right. But the difference between 6 and 2 is 4. So that would give me a net amount of water on the right side of the equation. 6 minus 2 is 4. So everything works out, everything checks out. So what I have to do now is simply determine the delta G for the overall chemical equation. So the delta G for the overall chemical equation is the sum of these 3 delta G values. So negative 1011 plus negative 142 plus negative 166. And when I do that math, I get negative 1,319. So that is the correct answer to question 13. So to summarize, reaction 1 was unchanged and the delta G remained at negative 1,011. Reaction 3 was also unchanged and that delta G remains at negative 166, but reaction 2 was reversed and multiplied by 2, so that delta G became negative 142. And then I added those 3 values together and I got my answer of negative 1,319. So again, this was a Hess's law type problem involving delta G values. All right, well, question 13 is the last question in this packet, so we have come to the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching.